Good morning, class. This is Today is September 27th, and this is the lecture for class on Tuesday, September 29th. And I've decided that we're not going to cover any new material today. We're just going to do a review ahead of the quiz, starting with going over homework 3, of course. And I'm here. Here I am. Hi. And I'm just going to sort of stay out of the camera so I don't mess up the focus while we go through the homework, and then we can turn the lights on and just go to the board. So let's just start with homework 3. And problem number 1 was it's sort of the previous homework, just doing things in reverse. And what you were supposed to do was look up the atomic mass and density of these 5 semiconductors up here, and you were supposed to then calculate the lattice constant based upon knowing how many atoms there are per lattice. So I did it in Excel. You take the atomic mass, which silicon, germanium, gallium arsenide, etc. For the compound semiconductors, you have to take the average of gallium and arsenide, because there's one of each, and multiply that times the mass of the atom and times 8, and that is the mass of a lattice unit. So that is the mass in grams of a single lattice cube. And then you look up the densities of these 5 semiconductors, and then, again, I just did it in Excel because it's very easy then. You just divide one by the other, and that gives you the volume of the lattice unit, and you can convert it to nanometers. I did it in nanometers here. And then you take that to the 1/3 power, and that gives you the lattice constant in nanometers. And so you can see that you get these 5 values for those 5 semiconductors. And then, this isn't really from figure 6.1. I looked them up, and it pretty much closely follows the values given there. And what's sort of interesting here is that the lattice constant, meaning the length of a side of a lattice cube, does kind of track with the atomic mass of the semiconductor, meaning as you go from lower to higher atomic masses, the lattice constant does get bigger, and so it is kind of like, the heavier the atom. It's not really bigger, because that's not determined by the weight of the nucleus, but basically, it kind of has to spread out a little bit, and so the lattice constant gets bigger. So that's kind of a principle that you can know here. Okay, so that was a pretty simple question, and then I asked you to read my paper on pseudomorphic crystal growth, and we had covered that. That's when you have a pair of layers, indium gallium arsenide and gallium arsenide phosphide. And so the idea here is that this one has a larger lattice constant than the gallium arsenide substrate, and this one has a smaller lattice constant than the gallium arsenide substrate. And I gave you this this formula that the lattice constant, the lattice constant of the alloy goes as the mole fraction, and the average lattice constant of a layer pair, where is it here? Oh yeah, is the sum of the products of the lattice constants and thickness of each layer divided by the total thickness. So you had to look up in my paper. I told you to do the 2 samples at the wider range. So basically, these numbers, actually you can look up or can come from problem 1, because you know the lattice constants of gallium arsenide and indium arsenide. I guess we didn't do the phosphides here, so you had to look that up. And so you find that the lattice constant of these materials, so for example, X here is the indium percentage, so this is the lattice constant of indium arsenide, and then for X equals 1, that becomes the lattice constant of gallium arsenide, and then this one here, you have to kind of realize it's backwards. Oh, I'm sorry, other way around. For X equals 0, the way that's 0.5653 is the lattice constant of gallium arsenide. Oops, that's a thing. And as X gets bigger, the lattice constant for X equals 1 becomes that of indium arsenide. And for gallium arsenide phosphide, for Y equals 0, it's that of gallium arsenide. And then as Y gets bigger, for Y equals 1, it becomes smaller, and for Y equals 1 becomes that of gallium phosphide. So these are your two materials, and it's like bigger, smaller, bigger, smaller, bigger, smaller. And the idea is that if you go bigger, smaller, that's what's called strain balanced or pseudomorphic growth, and you can do this. And so I ask you for these two samples, for X, these X values and these Y values, to calculate the effective lattice constant of the pair. And so that's given by this formula here, the lattice constant of the well, which I think some of you didn't realize. The well is the indium gallium arsenide, and the barrier is gallium arsenide phosphide. So you take the lattice constant of the well times the thickness of the well, which you had to look up from the paper, barrier times barrier, okay, divided by the well plus barrier. Oops. Okay, that's okay. And you get these values here. And again, I did it in Excel. And you can see it's pretty close. That basically the effective lattice constant of the pair for sample 1 was 0.5633 compared to the substrate 5653. And for sample 5, 564 versus the substrate 5653. And so, I mean, what I want you to remember from this is, well, I mean, I don't expect you to, I mean, well, actually, since the quiz is open book, you can, you know, do things like this. But, you know, the main thing to understand here is that, you know, I've taught you, well, let's save that for the review. So, you know, when we review epitaxy, we'll talk about basically the three types of epitaxy that we've gone over, where essentially it's unstrained if the lattice of the layer matches that of the substrate, strained if the lattice of the layer doesn't match that of the substrate, and in this case strain balanced when you grow an alternating set of layers to keep it in a lattice matched condition. All right, and then number 3 here, you know, I realized that when I have to do it over here. Okay, it's staying in focus. All right, so in the example in the textbook, he gives A by 10 by 10 centimeters. Now, I think he was a little unclear in the textbook, but I think I made that clear in the problem, that what he meant was that the area was 10 centimeters by 10 centimeters, or 100 square centimeters. And he uses sensitivities of his resist of 1, 10, and 100 microcoulombs per centimeter squared, and he gets these values for tau 1. And so the question is, what is the beam current? And so it's just simply rearranging this equation that he had in the textbook. He had tau is equal to AS over I, so you just solve for I. And, you know, I mean, what you should have found, I mean, you can plug in either 3 of these. If S is equal to 1, okay, then it's just, you know, A. You had to do it in the right units. 1 is in microcoulombs. Okay, so A in times the sensitivity in coulombs per square centimeter divided by the time he gave was 100 seconds. And that gives you 10 to the minus 6 coulombs per second. And you would find the same for the two other examples as well, of course, because they just go up by factors of 10 each. So for his example, to give the numbers he stated, the electron beam current has to be a microamp, 10 to the minus 6 coulombs per second, or 10 to the minus 6 amps. All right, so the question was, he says you can, in that same example, that you can do a pixel diameter of 100 nanometers. And the question is whether that's consistent. And I gave you the information, which you saw, could read in the text. The beam diameter goes roughly linearly with current. And so he says later that 2 microamp will lead to a 100 nanometer beam diameter. So 1 microamp should be 50 nanometers. Okay, now however, that is the beam diameter, okay, which is the diameter of the electron beam. If you go back to the figure, and now I'm going to go to the board and hopefully stay in focus everywhere. Remember, this is the electron beam. But then when it hits the photoresist, this is the substrate. This is the photoresist. All right. It scatters, the electrons, they scatter, and there's this effective diameter. Okay. So there's 2 diameters here. There's the beam diameter itself, and basically all the numbers work out that for his example, the beam diameter for 1 microamp should be 50 nanometers. Okay, but he says there, and okay, we didn't establish a number there, but he says there the scattering broadens the beam inside the resist, and the exposed area, that's this, the exposed diameter, if this is D, is much bigger than D. And so, I'll instruct the TA to, this was meant for you to go through the numbers and think about it. So, I'm going to instruct the TA to read what you wrote down, but to me, much bigger means more than 2. All right, so this means that this is greater than, if this is 50 nanometers, this is greater than 100 nanometers. All right, and he said that he could get a pixel diameter of 100 nanometers. So I'm saying that his example is not consistent with itself. Okay, so let's jump ahead to the review about e-beam lithography while we're on this. What the things I want you to remember again are, okay, that there's 2 things, all right, and we haven't really labeled them. There is D, the beam diameter, okay, and that is proportional to I, the current. And then there's the effective diameter, or the exposed diameter, which is much bigger than D. And I basically, those are the principles I want you to remember as far as e-beam lithography. And beyond that, I mean, there's so much more to know about e-beam lithography, but that, these things, and also the principle of S. S is the charge per unit area. The sensitivity. Okay, so at this point, I'm going to turn off the projector and start the review. So, uh-oh. Let's turn on this light. All right. Okay, here I am. All right, so let's go through a quick review. And let's see if we can't sort of put things all on the board, because that's always ideal if we can do that. So this is quiz 1 review. And for the quiz, as I stated earlier, there's going to be a set of multiple choice questions. So let's see if we can do this. Okay, so let me count here. 1, 2, 3, 4, 5. So I'm going to do this. I'm going to divide the board up. Okay, and this will do the divider too. And there's sort of 5 areas roughly that we've covered. And those areas are semiconductor physics, okay. Okay. Then film deposition. All right. Oops, I sort of did this wrong. Let me, well, okay, so let me do it this way. We'll put epitaxy over here. And so we're sort of going out of order here because we just kind of went over E-beam. And there's only a couple of things to remember there. Okay, and then optical lithography. And so we can divide the board up, and I'm out of focus. It worked, but somehow I managed to move things. Okay. All right, I'm starting to get a little bit of a principle here as far as that focus goes. Now, okay, so let's start walking through these one by one. So basically, in semiconductor physics, you learned about and I'm gonna avoid writing equations because the idea here is that well, let's just walk through it and see how it goes here. But you learned how you learned basically that the current density is the charge density, which I'm going to write as just for electrons E and N, times the drift velocity. So that's E N, and you learn that the drift velocity is given by the mobility times the electric field. And so that's sigma. All right, okay, and beyond that, we learned a few principles. Now, of course, we add in electrons and holes. Okay, and we learned that the mobility sort of goes as 1 over the defects, meaning, which kind of makes sense, that the higher the number of defects, the lower the mobility. And we learned about dopants. And we learned that there's acceptor atoms that give holes. And when they give a hole, they become, remember, they accept an electron to give a hole, they become negatively charged. And we learned that there's donor atoms that give us electrons. And then when they give those electrons, they become positively charged. And we learn that N times P, let's make sure we're seeing this. There's this wall here that I'm like up against, so I have to like scrunch up here. We learned that the product of N times P is always equal to the square of what's called Ni squared. And we learned that the intrinsic carrier concentration, that is what arises from, that's the carrier concentration, N and P, that occurs when we have no dopant, and that Ni is not proportional. I mean, this proportionality, I'm going to put a thing here. I mean, you know, it's not linearly with T, just like this isn't linearly with 1 over defects. But basically, because the intrinsic carrier concentration goes up, it occurs due to thermally ripping electrons off of the bonds, it gets higher with temperature. So that's it. I mean, now here, there's this whole charge neutrality thing, which we went through to how to calculate N and P, and I'm running out of board here. Well, I can write it down. I mean, charge neutrality is that P plus ND is equal to N plus NA, because the donors, when they give up their electron, are positively charged, so they're on the positive side, and the acceptors, because when they accept an electron, they become negatively charged on the negative side. All right, and that was, basically a whole the set of semiconductor physics that we went through that you need to know in order to do semiconductor processing. All right, and then we sort of, I'm running out of room, and we learned about crystals, which I'm just going to write down crystals, which include things like the first problem in the homework we just did. All right, and so might be a few questions on that. Now, okay, then we got to thin film deposition, and there's basically 3 things. There's evaporation, there's trying to think if I need to leave space here. There's sputtering, and there's chemical vapor deposition, which pretty much there's LPCVD and PECVD. And this basically is just throwing atoms down onto a substrate. And so that's the way to think about it. It just the atoms come down, they stick however they stick, and that's it. There's not much more to it. And sputtering, it's the same thing, okay, which is that, okay, atoms come down on the substrate, but you can do it one of two ways, right, where also there's a chemical reaction that can take place. So there's kind of, you know, A and B here. Now, I mean, I don't have room to write down all the mechanics of sputtering and evaporation, but remember evaporation, you're heating up a crucible of the material, and so it's evaporating, and I mean, I drew it, it's usually upside down, you know, the atoms come up, but that's the process. Sputtering, you're doing it in a plasma, because and so the ions in the plasma are what are knocking the source atoms off of the target, and knocking, and then they go flying onto the substrate. And remember, we went through how this one, they pretty much come straight down. This one, because it's a plasma, they kind of bounce around a little bit. And because it's in a plasma here, you can introduce reactive ions, and so get chemical reaction. And so, you know, this, you know, one sort of led us into chemical vapor deposition, where chemical vapor deposition, you know, you take this and you go all the way. You say, okay, I'm gonna put in a vapor of chemicals, which can either be simply heated, or they can be in a plasma. And these two main techniques, this one here is what's called stoichiometric, which, I mean, the important thing to realize is that for nitride, this one gives you Si, I forget the number, is it 3, 4? I always remember that. Whatever stoichiometric is, whereas this one, you can vary the ratio. And that's kind of the main thing to remember about that, is there's, of course, you know, just like in e-beam lithography, which we'll skip to epitaxy, but just like for e-beam lithography, there's a lot to know about all this. These are the main things I want you to remember. All right, and, you know, moving along here, this is pretty easy here, because epitaxy, you know, that's putting down crystalline layers. And the main thing I said, you know, MBE, which is molecular beam epitaxy, is like evaporation okay, but on a substrate at high temperature. So the atoms arrange in a lattice, i.e. a crystal. E. Okay, so there are other ways to produce, you know, crystalline layers to do epitaxy, but this is the main one in research labs, and what I wanted you to mainly be able to think about, because it's kind of easy. You learned evaporation. It's kind of the same sort of thing. It's just the substrate is at a very high temperature, so that when the atoms come down, they rearrange themselves and they fall onto the lattice of the underlying substrate. So, you know, that's the sort of first principle to remember. And let me do this onto the substrate lattice. That is, it's at a high enough temperature that, did I lose focus? It only works if, the problem is that I've learned that if I touch the camera, come on, you can do it. I really apologize for this, and I keep meaning, and I think I will have time this week to go explore this and learn how to fix it better. There we go. All right. All right, let's go on here. All right, and so going back to epitaxy here. So the point is that in epitaxy, the atoms come down, they're on a hot substrate, and so they find the lattice sites from the substrate, and so they want to grow at the substrate lattice constant. And so there's these three groups, it's where the layer, and what I'm going to do is I'm going to write it this way. I'm going to write A of the layer equals A of the substrate. And I'm not even going to try and attach words to this. I'm just going to, write down the three things that can happen. You can have where the layer's lattice constant equals out of the substrate, and that's very, very happy, of course, because then it just grows and you can just do whatever you want. Okay, there's where the layer is not equal to the substrate. Okay, and for that there's a thickness limit. Okay, meaning you can grow up to a certain thickness, and so the layer is growing and it's trying to stay at the substrate's lattice constant, and it's trying, and at some point it says, no, I can't, and so it basically creates defects. However, it needs to do that in order to relax itself. After which, after limit defects. All right, and then there's three. There's where A of a pair is equal to A substrate. Which that's our homework 3, problem 2. Okay, and I didn't want to belabor that. It's just that I wanted you to be aware that there's that third type, okay, which is called strain balanced or pseudomorphic. Skipping, no, well, not skipping, but now going to EB morphography. We just covered this. There's the beam diameter, D, which is proportional to the beam current, I. All right. And there's the sensitivity, which is the charge per unit area to forward exposure. And so the exposed area is much larger and that's all I wanted you to to have for that for now. My focus has gone a little bit, but it's just good enough that we can keep going here. Okay, so for E-beam lithography, now you know that's sort of kind of the little few principles I want you to remember, but also what it is for is for direct writing of features. So basically, you have this E-beam, and you just you can raster it around on the substrate and turn off turn on and off the E-beam and basically make whatever pattern you want by direct writing. And so the reason to know these principles is because because it's direct writing, a lot of the consideration is how long it's going to take. And so now also the exposed area, well, okay, so let's just leave it at that, but I'm just going to say in words that you can try and increase the you can try and increase the speed, or say it this way, you can try and decrease the writing time by increasing the current, but that'll increase D. Okay, and remember that's because of Coulomb repulsion in the E-beam. You can try and decrease the time by decreasing S, meaning requiring less charge. But if you do that, then this exposed region gets wider. Okay, so it's this engineering optimization of, okay, how fast does it need to expose based upon the area and the time you have, in the E-beam writer and stuff like that. You can choose, and how fine your features have to be. So the message is basically that the finer your features, okay, the larger S is going to have to be, and the smaller I is going to have to be. So both of those, so to kind of the finer your features, the time it takes to go up kind of as the square. All right, so if you remember those principles, you'll be fine there. All right, now I'm going to go over here and keep an eye on my camera. So now if I stand over here we can cover optical lithography. Now, optical lithography, I mean, here, I mean, it's just the steps. All right, so one, you spin photoresist on the wafer. Okay. Two, you pre-bake to evaporate solvent. Meaning the photoresist, that's basically a mixture of the photosensitive chemicals and the solvent. And let me see something here. Okay, you can see it. I don't want to mess with my camera. Okay, and so you take your wafer, you spin on photoresist, and you pre-bake to get the solvent out. Then you have your wafer ready, and then three, you load wafer and photomask. And the mask liner. All right. So the mask liner, that's this machine that basically you can put your photomask in, and you can put your wafer in, and you can align the wafer to the photomask, expose, to UV light in the mask aligner. You put in developer, and so in the developer you develop, okay, for positive resist it removes the resist that where you've exposed it. For negative resist it removes the resist where you haven't exposed it. And 6, you rinse and dry. And then basically what I'm going to do is I'm going to put 7, you post bake for etching steps. Okay, so I put that in parentheses because that's an optional step that you only do if the resist is meant to be what it sounds like, which is really resist something like etching, like in an acid bath or something like that. For example, if you're doing liftoff where the photoresist stencil is just meant to be a mechanical thing, all right, you don't do number 7. Okay, not for liftoff. And so that's why that's in parentheses. Okay, so that worked out perfect. The board is filled. That is what is going to be on the quiz. We did talk about projection lithography, where you have an optical system that instead of having, this is basically contact lithography. Okay, and that's what you do in your research lab primarily. So if you have projects here at the university, you're going to be doing contact lithography. I wanted you to be aware of projection lithography, and in particular a couple of optical principles that I went through. You have not had any homework on any of this. The homework stopped at e-beam lithography. But the main thing here is I just, I want you to understand these steps. Watch the video of Nam, performing this, so you have a nice feeling for how it's done. It's really more of, okay, I want to convey here no mathematical principles, so to speak here, but the sort of step principles of what you do to do optical lithography. And that's it. Okay, so that's the extent of today's lecture. I'm going to slide around here so I don't mess up my focus. So basically, you can kind of look at this board here, and as long as you followed everything I've said, you should be ready for the quiz. And my focus stayed pretty good. I did lose it a little bit, but I think everything's there. Again, you have to, listening. I wish I had better handwriting, but it's all there. And okay, so we'll talk about this. Okay, so now you have it there and you can actually use that as kind of a screenshot. I should figure out. I think there's ways of making something the little icon that you see on YouTube, but okay, you get the idea. So you can sort of just you could take a screenshot of that and print it out, and now you don't really need it as not a bad idea to take this screenshot and print it out for when you take the quiz on Thursday. Again, the quiz is completely open book. It's a set of multiple choice questions. However you need to prepare for it and be prepared for it during the quiz. My attitude in teaching is that it's much preferable to me that everyone gets every answer right and everyone gets an A. That is the ideal situation. So good luck, and I'll talk to you tomorrow during the chat session.